Welcome to POE Thermodynamics Practice Problems. So here we have a block of aluminum at 80 degrees placed in 1 liter of water at 25 degrees. Calculate the energy transfer to the final temperature becomes 30, and then calculate the mass of the aluminum. So the first thing you have to do is write down your values of what you know. Let's make a list of our values. Okay. So our initial, both, neither, and our final temps. All right, let's put in what we know. So the temperature of the aluminum initial was 80 degrees C. Temperature of the water initial is 25 degrees. This is 80. That's an 80. All right. The mass of the aluminum, we don't know. Mass of the water is 1 kilogram. Tells us that right there, 1 kilogram. Our energy transfer Q, I'm not sure what that is. We got to figure that out. That's what we're solving for right here, energy transfer. All right. What is the specific heat of aluminum? All right, so looking at specific heat on a line, we find out that it's 900 joules per degree Celsius. And the specific heat of water, we know, is 4184. Again, those come from just charts on the internet. And that's going to be Celsius. Right. And final thing, what's the final temperature of the aluminum? Aluminum final is, we know it's going to be 30 degrees Celsius. It says that right there. And of course, the final temperature of the water is also the same. All right, so those are our known values. Let's look at our formulas, what we're going to be using. So for the transfer of energy on our chart, we're going to be using Q equals MC times the temperature change. So let's write that down. We know that the change of our heat transfer needs to equal 0. Right? Because whatever happens, you can't gain or lose any energy. It has to go somewhere, so all the heat is going to go somewhere, which means that the change of the water energy is going to be added to the change of the aluminum energy, and that should equal 0, assuming that we don't lose any heat to the air. So we're just going to assume that. Okay? And let's make sure, let's solve for, try to figure out what the energy transfer of the water is. So we'll move the Q of aluminum to the other side, and we'll start with that. All right, so let's solve for A. Part A up here says calculate the energy transfer if the final temperature becomes 30 degrees. So we'll come down here and we're going to use the formula that I pointed out on your sheet. So the the energy transfer of the water is going to be equal to the mass of the water times the specific heat of the water times the temperature change of the water. Let's substitute what we know. We have 1 kilogram of water. Specific heat of the water is 184 kg times C over J. And the temperature change, well, we started out at 30 degrees Celsius. Sorry, we ended at 30 degrees Celsius and we started at 25 degrees Celsius. So really that's just going to end up being a 5. All right, multiply all that out. And the energy transfer of the water is going to be 20,920 joules. And how do we get joules? Well, if we look up here, our Celsius is up in the air, so those are going to cross out. Our kilograms are going to cross out, and that leaves us with our joules. Okay? So now that we know that is how much energy went from the aluminum into the water, okay, because they're equal. Whatever energy comes out of the aluminum has to go in the water, so that went into the water. So let's solve for B. Now that we know Q, we can figure out energy transfer for B. So we have same formula, equals minus Q of the aluminum, and we know what one of them is going to be. Let's put everything in there. Equals minus mass of the aluminum times the specific heat of the aluminum times the aluminum final temperature minus the aluminum initial temperature. Right? Fill in what we know. We know the energy transfer was 20,920 joules. That came from right there. And that's going to equal minus, we don't know the mass of the aluminum, but we do know the specific heat of aluminum is 900 joules per kg Celsius. And we know the temperature change was 30 degrees at the end, minus 80 degrees in the beginning. Okay, let's do a little math. We end up with 45,000. Multiply these together. You get 45,000 joules per kg. All right, and we're going to move this to the other side, so that's going to be MA to make that positive. That's going to equal 20,920 joules. All right, now why do we lose Celsius? Right here, you got to cross out the Celsiuses, so we don't have those going with us. All right, now we need to get the MA by itself, so we're just going to divide both sides by 45,000. 45,000. Okay, let's do some, this will cancel itself out. Look over here, the joules are going to cancel out, so that gives us kg equals mass of the aluminum. Divide that out in your calculator, and you get 0.465 kilograms is going to be the mass of the aluminum. All right, problem number 2, 250 gram piece of copper metal at 100 degrees is placed in a 0.8 liters of water at 22 degrees. What is the final temperature of the water? All right, again, let's write down our values. All right, it's the things that we know. So our initial, our both or neither, and our final. All right, I'd like to make a little chart. So what's our initial temperature of the copper is 100 degrees. The initial temperature of the water, right, water initial, is 22 degrees Celsius. The mass of the copper is 0.25. We got to change it to kilograms. All right, so that's where we're grams to kilograms. Our mass of the water is equal to 0.8 kg, 0.80 kg. And then we have the specific heat of copper is 386, very different from aluminum. And that's joules kilogram times Celsius. And specific heat of the water is 4184 joules kilogram Celsius. All right, so we know that. All right, what we need to know is the final temperature, temperature final, okay? And that is going to be equal to the temperature of the copper and the temperature of the water. All right, so when you put those together, that's going to be the final, because everything's going to be the same temperature. All right? Just like before, energy transfer needs to be 0. We're assuming that all the heat in the system stays in. We don't lose any to the atmosphere, the air, anything around there. Okay? So that means that the energy transfer of the water plus the energy transfer of the copper is going to equal 0. And if we're going to be solving for one of them, let's move for just fun, the copper to the other side. All right, let's start doing some solving. This time what we're going to do is we're going to use the whole formula. It's on our formula sheet right there. We're going to use that for both sides. So mass of the water, specific heat of the water, times the temperature change of the water is going to equal minus the mass of the copper, specific heat of the copper, and the temperature change of the copper. Okay, I'm going to try and keep my equal signs in the middle as we go back and forth. All right, So mass of the water, let's spread this out. And we actually have the temperature final minus the temperature of the water initial. Well, that should be a W there. It's going to equal the mass of the copper, specific heat of the copper, the same thing. Temperature of the copper final minus the temperature of the copper initial. So I like to kind of write it out so I know where to stick all my numbers. So let's fill this in. So we're going to have 0.8 kilograms of water. Specific heat of water is 4184 joules kg times Celsius. And our temperature change was water final minus 22 degrees Celsius. It's going to equal, oh, my equal signs are moving, that's okay, 0.25 kg of copper times 386 joules of copper times temperature final minus 100 of copper. All right, we got a whole lot of stuff. So let's start crossing some things out. So we can go through here. All right, we can cross out kilograms because those are going to cancel out. And let's start doing some multiplication. Okay. We're going to multiply these together and we're going to get 347.2. That's going to be joules over C. And we still have the original, or the final temperature of the water minus 22. And that's going to be equal to minus 96.5 joules over Celsius times the temperature final of the copper, oh, forgot my little C up there, minus 100 degrees Celsius. Okay, and then what do you have to do next? We're going to distribute this across. So we're going to get 347.2 joules Celsius, all right, times the final temperature of the water minus 73638.4 joules. So I multiplied that times this, multiplied that times 22. That's how I got 73,000. Do the same thing over here, distribute. We're going to get minus 96.5 joules there, plus the temperature final of the copper, plus 9,650. So I multiplied the 96 here times the 100 to get that. All right, and that's going to be joules because the Celsiuses are going to cancel out. The Celsiuses are going to cancel out. All right. Now what we want to do is we're going to move the 96, so we're going to add 96.5, add 96.5, both sides, they'll cancel out, and we're going to be left with 3.7 joules there, so we add those together, minus 73638.4 joules. That's going to be equal to 9650 joules. Oop, forgot. I'll be adding those together. I messed up. This doesn't go here because this follows over there. Yep, sorry, I messed up. This parentheses is not supposed to be there. So there, that's supposed to go over here. So those go together. All right. Work this out. We add 73,638.4 to both sides. All right, those cancel out. And then we divide it by that, and we are left with 24.2 degrees Celsius as our temperature. All right, welcome to number 3. We're going to calculate the energy transfer in a wall section measuring 2 by 1 meters and 0.04 meters thick with a thermal conductivity of 0.1 joules seconds meters Celsius. What that means is that's how fast, thermal conductivity, how fast the energy can flow through a substance like the wall here. Opposing sides of the wall have a temperature of 10 and 5 degrees Celsius after 1 hour. As before, let's write down what we know. So our initial, our values, and our final. Well, we know our initial temperature, Ti, is 10 degrees Celsius. We know our final temperature, Tf, is 5 degrees Celsius. We know what the area is, 2 meters by 1 meter. So you multiply those, you get 2 meters. We know our constant, 0.10. That's joules second meter Celsius. We know the thickness of the material, represented by L, 0.4 meters. And we know the change in time. That's 1 hour. And that's equal to 3,600 seconds. And we also know that there's a change in temperature. All right, that's 10 degrees Celsius minus 5 degrees Celsius, which is going to give us a total difference of 5 degrees Celsius. Those lines a little longer. I think that's about all we know. So, some things to solve for. They're asking what is the rate of temperature change, and that deals with time, like how fast does the energy transfer through the wall in 1 hour. So, let's put that down here. That's going to be represented by P. P is the rate of heat transfer, and they also want to know how much thermal energy, so that's represented by Q. Let's look at our documents here. We're going to be using this formula. We have our area, our constant, time, thickness, and then up here we have what P is equal to, energy transfer over time. So we're going to be using those two formulas. So let's write those down. P is equal to, let's move that up so you can see it, the thermal energy by the change of time, and then P is also equal to how thick the material is, or sorry, the constant, the thermal conductivity right there, thermal conductivity, times the area, and then times the change in temperature, and put all that over however thick the material is. Obviously, the thicker the material, the longer it's going to take. Okay. Let's solve for Q, so we're going to change this around. So we'll move the Q over here, and that's going to be the P times the change in time. All right, and then let's substitute P. So put in the P formula right there. He said P. So Q is going to be equal to the K times the area times the change in temperature. Put all that over L. All right, and that's going to get multiplied by the change in temperature, time. All right, change in time. So this is the formula that we're going to be working with right here. We got that by combining those other two formulas. So let's do some substituting and solving. All right, so Q is going to equal 0.10 joules, seconds, meters, Celsius, times the area, which is 2 meters cubed, times the temperature difference, which is 5 degrees Celsius. All of that gets put over the thickness of the material, 0.4 meters. This whole shebang is going to get multiplied by 3,600 seconds. Okay. Let's do some crossing out. Okay, right away, we can cross out one of the meters here and the other meter there. We can cross out Celsius right there and there. And we can even cross out seconds because we got seconds over here and seconds over there. Okay, let's multiply this out. We're going to be left with, that's going to be 1. I know, nice easy number, over 0.04. All right, that's actually got to bring down the joules. And that's going to get multiplied by 3,600. All right, multiply this out, or divide this out, sorry. You're going to get 25 times the 3,600, and we end up with 90,000, there's a J in there, joules. And that's going to be equal to our Q. So that's how much energy is going to pass through that wall in 1 hour. All right, welcome number 4. Determine the R value of the wall cavity. In order to get this, you're going to be using this chart. Okay, so you can look at like fiberglass battens right here, and you come down here and you find fiberglass batten is 3.142 R value per inch. And if you look, this is 6 inches long. So you're going to have to multiply that 3.142 times 6. All right, so I'm just going to give you the numbers. We're going to do the wall cavity first. All right, the wall cavity is this pink area, like right here, because this area is different than down here where there's a piece of wood. So we're going to figure this out first. All right, first thing we have is drywall. All right, if you look at your chart, drywall is 0.56 for 5/8 inch drywall. Fiberglass, we just talked about, and that's going to be 3.142 times 6 inches. And that's going to give you an R value of 18.9, so we're just going to round it up to 19. Okay? And then our foil face styrofoam, real fancy stuff. It's got a nice high R value of 7.2. And this stuff works really well, 7.2. Zoom in a little bit there. Let's move on. Air. Well, they give you the air. Right there, airspace is 0.17. Okay, and then we got some brick. Now the brick, okay, they give you some measurements here. So let's look down here. So we got a brick drawn out. Okay, it's going to be 8 inches that way, and it's 3.5 going this way. This is the direction that the energy is going to go through to get through the brick. All right, so that's how you figure that out. So we're just going to use a brick that's 4 inches. So we're going to use a brick that's 4 inches, and that's going to be 0.8. Okay, all you got to do, add those together, and that's going to give you your R value. So add all those numbers together. Now, not only do we have a wall cavity, we also have where the wood stud is located. Okay, so we're going to use the same things. Again, we have drywall. We're down here now, so we're going through this area. So we have drywall, that's 0.56. We have the 2x6 wood. And if you know that, if you look at it, wood is 0.94 per inch, and we have 6 inches, so that's going to give us 5.64 for an R value. Okay, so that's going to be our R value for the wood. And then we have the foil face again. That's going to be 7.2. We have our airspace. That's going to be that. And then we got our brick again. So a lot of these numbers are going to be exactly the same, 0.80. Once again, R values, you just add all of them together. So add those together to get your final answer. And you will get an R value of 14.37. And then for the wall cavity itself, you're going to get an R value of 27.73. So what that means is, up here where you don't have wood, it's going to be a better insulator than down here where you have the piece of wood. All right, this is usually the bottom of a wall, so it's very small. Okay, so that's how you get the R value of materials and its ability to resist the flow of heat. Problem 5, radiation. Prior to dressing for school, the student watches the morning weather decide what to wear. The bedroom is 65 degrees and the student's skin is 94 degrees Fahrenheit. Already that's kind of stinky because we have to convert that. Determine the net energy transfer from the student's body during the 15 minutes spent watching the morning weather. Note, the skin's emissivity is 0.9 and the surface area of the student is 1.3 meters squared. All right. So, as before, we're going to write down our values. Okay, now this is a little different because we're doing radiation, so we don't really have an initial and a final. We're just trying to figure out how much energy gets transferred out. All right, so we're not raising or lowering any temperatures. We're just going to assume that the room is cooling off as fast as the student's body is heating it. So let's look at some of our values, and we're going to start running low on room here. So let's start with the easy one. Area A, 1.30 meters cubed. All right, the area of the student's skin. The emissivity, okay, they give that to you, is 0.90. That's E. All right, what else do we need? We know the bedroom temperature. We're going to call that, let's say, T1. That is 65 degrees Fahrenheit. Ugh, I hate that Fahrenheit. Skin temp, call that T2. That's equal to 91.4 degrees Fahrenheit. Okay. How long they're in the room, so time, is 15 minutes, which is equal to 900 seconds. We know that. We also learned about, for radiation, Stefan's constant. Oops, spelled that wrong. Stefan's constant, all right, that is equal to 5.6696. By the way, this is on your reference table. 10 to the negative 8. All right, that's watts over meters squared times Kelvin to the 4th. Okay. Well, before we even get started, we got to convert those to Kelvin. So I'm just going to come over here. I'm going to call this Fahrenheit to Kelvin. This is going to be a bit of a problem, so let's get started on that. If you look on your reference table, there's an area with your conversions to go from one to the other, so we're going to be using that. All right. So first thing we have to do is transfer this Fahrenheit to Celsius. So temperature Celsius is equal to temperature Fahrenheit minus 32 divided by 1.8. So TC is going to be equal to 91.4 degrees, the skin temperature, minus 32 divided by 1.8. Now that's just a straightforward math problem. So the skin temperature is going to be 33 degrees Celsius. Now to convert Celsius, we need to add 273. So to get temperature Kelvin is temperature Celsius plus 273. So 33 plus 273. And when we're all done, we're going to get 306 degrees Kelvin. And that's going to be our skin temperature, which is temperature 2. Do the same exact thing to figure out temperature 1. And all right, instead of you going through everything with me, I just did it again. There's the formula, same steps. So we have our TK for Kelvin, and it's actually number 1. That's our Kelvin for number 1, our Kelvin for number 2. Let's start solving some problems. Okay. Next, we're going to be looking at our formulas. Okay, see which formulas we're going to be using. We're going to be using the rate of heat transfer net gain. All right, we got Stefan's constant, we got our area, we got our temperature change. All right, and we're going to be using this guy up here also, the change of thermal energy over time. So let's write those down. Okay, what we're looking for, we are looking for P, which is the rate of energy transfer. And we're looking for Q, which is the energy that's getting transferred into the room. So we want the rate of how fast it leaves the person and gets in the room, and we want to know how much is going to be transferred total. All right, let's move on. This one we know, so P is equal to the change in our energy over a little bit of time. Let's solve for Q though. Solve for Q, and that's going to give us change in Q is equal to the P times that. Okay? We also need the P net. That's going to be, that was bad, Stefan's constant, the area, and the emulsivity. And that's going to be multiplied by the temperature change. So we need T2 to the fourth minus T1 to the fourth. And we're going to have to solve for all of this. So let's put in our Kelvins. Let's solve for this part first. All right, so we're going to solve for the T2 first. All right, so T2 to the fourth minus T1 to the fourth. All right, since we know those numbers, we can work with that first. So we have 306 Kelvin to the fourth power minus 291.33 Kelvin to the fourth power. This is where the Desmos calculator can come in handy. Multiply that out. We get 1.564 10 to the 9th power Kelvin to the fourth power. Okay, so that number we need to put in our back pocket as we move on to the next step. All right, let's put down our P net. So we'll just come over here. So here's our P net formula. Let's do some substitutions. So P net is going to equal Stefan's constant, 5.6696 times 110 to the negative 8th. That's going to be watts over meters squared, Kelvin to the fourth. All right, that's going to get multiplied by 1.3 meters squared. That's our area times our emissivity, which is 0.9. So we got 0.9. And that's going to get multiplied by the number we just got, which is 1.564 times 10. Oh boy. 9th K4. We're running out of room. Anyway, so move all that over. All right, we're going to move all that over. First thing I'll do is I'll just combine those two. So we'll just shrink everything down. All right, 5.6696 times 10 to the negative 8th watts over meters squared Kelvin to the fourth times. Multiply those together, and we get 1.1817. And then we have the number over here, which is our temperature, 564 Kelvin to the fourth. Now we got a little more room. All right, so multiply out this formula and do some crossing out. All right, if you notice, we got Kelvin to the fourth. You can cross out Kelvin to the fourth. We have, oh, I forgot my meters squared. We got meters squared there. So that's going to get crossed out, meters squared there and there. And that's going to leave us with our watts. It's going to leave us with our watts. So if you have a Desmos calculator right here, you can see on the left, I entered all that information in, that whole formula. You can type in the whole formula. You can probably do it in a graphing calculator too. And then it gives us an answer of 104.98. So our P net is going to equal 104.985 watts. All right, here's our watts right there. That gets brought down. So that's going to be our P net. So that's how many watts of power the person is, gave off over the time. But we want to know the how much thermal energy that is. So that's watts. We want to turn it into some joules. So we're going to do our Q formula, P, and then how much time elapsed. So Q is going to equal to 104.985 watts times, and our time is 900 seconds. All right, multiply that together, and we're going to get 94,486 joules. So that's how much heat, or joules, that's how much joules the body puts off just sitting there for 15 minutes. All right, remember, 1 joule is equal to lifting an apple about a meter. Okay, there you go. The big problem